Hey guys, this is Mr. Marchman, and I'm going to talk to you a little bit today about how to solve some problems using rotational kinematics and rotational kinematic formulas. And so let's go to our sheets and let's take a look at the connection between the formulas that we've already been using this year and how they relate to rotational motion. So if you think back to your translational motion formulas, I typically think of sort of two or three big formulas that stick out. Translational motion, I think of this formula. It says the final velocity equals the initial velocity plus acceleration times time. I think of this formula that says delta x equals vi times t plus 1/2 at squared. And I think of this formula. Those are sort of my big three formulas that I can, and there's other ones that are manipulations of those, but those are my big three. Well, in rotational motion, the same formulas exist, only we need to use rotational quantities. So for instance, wherever I see a v, I'm going to use an omega. Wherever I see an a, I'm going to use an alpha. Wherever I see a delta x, I'm going to use delta theta. So the first equation has an analog in the rotational motion that looks like this. The final rotational velocity, or angular velocity, equals the initial angular velocity plus the angular acceleration times time. This formula also has an analog in the rotational motion that says the angular displacement equals angular velocity, initial angular velocity times time, plus 1/2 angular acceleration times time squared. And same thing can be said here. The final angular velocity equals the initial angular velocity squared plus 2 alpha times delta theta. And so these formulas have the same properties that these had. Remember, these all assume constant. They all assume constant acceleration. So in this case, alpha over here, right? These assume constant acceleration, constant linear acceleration. But the formulas work the same way. So for instance, here I have David spinning a rock at a constant velocity of 60 revolutions per minute. What is the stone's tangential speed? This one doesn't actually use those. I'm not sure why this is in there. But here we have David spinning this rock. Let me get a better sort of understanding of what's happening. Here's his rock going around in a circle. If you think about that rock being sort of right here, what is its tangential speed? So how fast is it going right here? Well, we know it's traveling around like circular motion. Its rotational velocity is 60 revs per minute. All right. What is its tangential speed? We know that the tangential speed is equal to r omega. Well, I want to write this in terms of radians per second, just simply because that's how I'm used to writing my angular velocity. So if I want to convert 60 revolutions per minute into radians per second, I need to do a little conversion here. So 1 minute, there are 60 seconds. So now I've gotten rid of my minute. And then I want to get rid of my revolutions. So I know that 1 revolution is 2 pi radians. And so notice that I'm now left with radians per second. And so when I multiply 60 times 2 pi and divide by 60, hey, look what I get. I get 2 pi, which is about 6.28 radians per second. So now, take this. I get Vt equals r, which is 1 meter, times 6.28. So it has a tangential velocity of 6.28 meters per second. let's do the next one. Carpenter cuts a piece of wood with a circular saw. The saw blade accelerates from rest with an angular acceleration of 14. So alpha is 14 radians per second squared. The initial angular velocity is 0 radians per second. To a maximum speed of 15,000 RPMs. So let's say that's the final angular velocity, 15,000 revolutions per minute. What is the maximum speed in terms of, or in radians per second? So we're going to do a little unit conversion here. If we go back to my unit conversion, 1 revolution per minute, right, is equal to, okay, 1 revolution per minute. I'm going to get, to do the conversion, I need to multiply by 2 pi radians and divide by 60 seconds. That's essentially my little shortcut. So I need to multiply by this quantity here. So omega f equals, I do 15,000 times this quantity, and that gives me 1,570.8 essentially radians per second. I want to figure out how long it takes it to reach its maximum speed. Well, I'm looking for time. So I know it starts from 0. Let's use this. 1570.8 equals alpha. Oops, alpha I know. Alpha is 14 times time. And so divide that quantity by 14, and that should give me 112.2 seconds. Is the time it takes for that saw to get up to its maximum speed. So here we have an object begins at rest. It begins to rotate with a constant angular acceleration. I want to figure out how far does it rotate in time 1/2 t. So here's my view of this thing. Let's say it's rotating this direction. Let's say it starts off here, make it easy, and then it rotates some angle theta. So it's rotating this direction, and this is theta. How far does it rotate in 1/2 t? So in half that time. Let's look at this. I know that this is true. If it starts from rest, then this is true. Yeah? Well, let's just say that it starts at 0, so theta equals 1/2 alpha t squared. Let's see what happens when I plug in half the time. So we'll call this theta. Oops, we'll call this theta 2. 1/2 alpha times 1/2 t squared. Well, if I factor all this out, I get 1/4 times 1/2 alpha t squared. That equals theta 2. Well, this quantity here was just theta 1, right? So I will then, that means I will have rotated 1/4 of the total distance that I would in the total time t. There you can see a good explanation of that there. Okay, here we have a wheel that rotates at constant angular acceleration. If the angular speed of the wheel is 2 at time equals 0, through what angle does the wheel rotate in the first 2 seconds? I'm just going to give the answer in radians. I don't really care too much about revolutions. So it has an initial angular velocity of 3.5, of 2. Initial has an angular acceleration of 3.5. I'm looking for the angular displacement. The angular displacement in the first 2 seconds. So here we go. I would use this. And that gives me four plus 7. So theta equals 11 radians is how far it rotates in those first 2 seconds. If I wanted to find the angular speed after those 2 seconds, that is simply that. I know it starts off going at 2, has a acceleration of 3.5, and so my final angular velocity is going to be 9 radians per second. There we go. Okay, and the last one on here is this quick trick here. So here we have a graph. This is a graph of angular velocity versus time. And as you can see, and as you can probably sort of understand from your intuition, is that this graph is going to have very similar properties to the graph of that we looked at before that showed, velocity in time from the first chapters or first part of this year. So the slope of this is going to the slope of this told us the acceleration. The slope of this will tell us the angular acceleration. The area underneath this curve here told us the displacement. The area underneath this curve is going to tell us the angular displacement. So here we go. They want to know how many revolutions does the wheel make in the first 4 seconds. How many revolutions? What is that going to be referring to? The number of revolutions is going to be telling us some sort of measure of theta, what is the angular displacement. If we look at our units here, this is actually not measured in radians per second, but this is measured in revolutions per second. So I'm looking for the area underneath this curve. If this was measured in radians per second, I'll still be looking for the area, but then I would need to do some sort of conversion from radians into revolutions. But this is going to make it easy for me. So I'm measured in revolutions. So let's see how many revolutions are in the first 4 seconds. So for me, I'm going to divide this into a triangle and a rectangle. The area of this first portion is 1/2 the base times the height. So 2 revolutions here. 1/2 the base is 1 times the height is 2. And here we have a area of a rectangle, which is 4, and so I get the object undergoes 6 revolutions in the first 4 seconds. Well, I hope this helped sort of give you some perspective on how to solve these types of problems. Really, these are very easy as long as you can make that connection between the translational motion problems and the rotational motion problems. If you can keep those 2 things straight and use similar language and similar understanding for both, then that should help you as we move forward in this section. Good luck.